thought maybe example 2 was challenging enough to maybe, I thought that I would put a video together for you to review this while you're at home, students. So example 2 says, evaluate the Riemann sum for f of x equal to x cubed minus 6x. Take sample points to be right-hand endpoints with a is equal to 0, b is equal to 3, and n is equal to 6. So with this in mind, then I'm first going to think about, well, what is the Riemann sum? So if you remember the Riemann sum, the Riemann 6 is going to equal the summation from I is equal to 1 to 6 of f of x sub I times delta x sub I, or just delta x. In this case, delta x will be the same. So, and delta x is equal to 3 minus 0 over the 6 subintervals that you see. And that will be delta x is equal to 1/2. So we have delta x is equal to 1/2. Now, what we're going to do is we're going to split up this subinterval with right-hand endpoints. So you can see the right-hand endpoints. R6, here's an endpoint, 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 endpoint. And we have a function, if I can put the table of values just so that you see this. If I look at the x values and then the y values, if you will. So I'll start with 0.5, 0.5, that will be right here. And the 0.5, 1, 1.5, 2, the function values then are going to fill in the table, and 3. Okay, so I'll fill in the function values in the table. And so the function value of 0.5 is negative 2.875, negative 2.875. The function value of 1 is negative 5 when you plug them in the function. 1.5 is negative, the function value is negative 5.625. And the function value of 2 is negative 4. The function value of 2.5 is 0.625. And the function value of 3 would be, of course, 9. So you have those values at the right-hand endpoint that you need. I'm just going to write them up here. So I go negative 2.85 for the height here, negative 2.875, negative 5, negative 5.625, negative 4, and then I have 0.625. So I'm marking down the heights of each of these rectangles, some negative, some positive. Okay. So then to get the summation, I have enough room down here, the summation. Let me just correct that. I'm going to say R6, just to carry all the notation with me. So R6 then is equal to the summation of all the f of x sub i's, and that's these guys, f of x sub i's times delta x, which is the same from I is equal to 1 to 6. So we're going to start listing them. Remembering that the function is x cubed minus 6. So R of 6 then is equal to, and we're just going to list them as negative 2.875. That would be the height of the first rectangle. And remember, it's a negative height. It's below the x-axis. Times 1/2. Times 1/2. That we get the area of the first one. Plus, we have negative 5 times 1/2. Plus, negative 5.625 times 1/2. Plus, where did that leave me? Negative 5.625 times 1/2 plus negative 4 times 1/2 plus 0.625 times 1/2 plus, then we have 9 times 1/2. So adding all those together, we get R6, the approximation, would be equal to negative 3.9, negative 3.9375, negative 3.9375. Now, usually if it was the AP exam, you would round to 3 digits. Just with rounding, some of you need to think about that, that would be equal to negative 3.938. Okay, just because the AP is traditionally 3 decimal point rounding. Okay, so that's the first part. Let's take a look at the second part then. So we have an approximation with 6 rectangles. Again, negative area below the x-axis and positive area above the x-axis. So we want to evaluate the definite integral by using Riemann sums. Okay. So with this one, a little bit different. We're going to be looking at R sub n, and R sub n then is going to equal the limit, because this is the definite integral. The limit, as in, by definition, the limit as n approaches infinity of the summation from I is equal to 1 to n of this idea of f of x sub I times delta x. So we have some expressions that we need to utilize. And again, a real quick sketch of this so you can see that, here you have this part of the function that's underneath and part of the function that comes up above. So we're looking at part of the area being negative and part of the area being positive on a simple sketch of the graph. So let's color, maybe we'll put that area as red for negative. Positive. Okay, so, and if we look at this, we first need a delta x. So we start off with our expression in our integral where we want to say, okay, this thing needs to be clarified. It has an x sub I and a delta x in it. So when we go to look at delta x, we go to the end of the interval, which we know is at 3. And then the beginning of the interval is 0. So delta x will be b minus a over n. So our delta x turns out to be 3 over n. So put that here. Then we need to understand this idea of what x looks like, x sub I. And so instead of just jumping right into the problem and saying that, okay, x sub I is equal to the start plus delta x times I, what I'm going to do is show you that if you start, you're starting at a is equal to 0. Then you have 0.5, 1, 1.5, 2, and 2.5, and 3. Kind of squeeze it in there. I can move it over just a little bit. Everything go with me here. There we go. Okay, so 2, 2.5, and then finally 3. So as you're moving along now, you got to remember that these, I'm going to be considering smaller intervals. So now forget for a moment that we're using all of these 0.5 and the same interval. Okay, let's picture that there's kind of a break in the middle, kind of like you would do on a graph, and say, this is not really what it appears to be, and I'm going to say that if this is a delta x and this is a delta x, and they're infinitesimal, meaning very, very, very small, I want to talk about what my x sub i's would be. So in the beginning, I would talk about this x sub I, x sub 0, if you would. Do I want it to be x sub 0 or x sub 1? I think for the purposes here with a right endpoint, this is going to be x sub 0, and then I'm going to make this x sub 1 and x sub 2. And then keep in mind, we're going to go all the way out to where we have 3 is going to be our x sub n. X sub n. So that if I look at delta x, if you picture this, x sub 1 x sub 1 is equal to 0 plus 1 delta x. Oops, x sub 1. X sub 1. Silly teachers. So we have x sub 1 is equal to 0 plus one of those delta x's. But x sub 2 then is equal to the start plus 2 delta x's. And so on. We could say x sub 3 and x sub 4, x sub 5. So when we look at our x values, they're going to be governed by how many times we add delta x. So x sub I will always be where you start on the interval. So that's always going to be a, and then you're going to add delta x I times. So you're going to multiply delta x times I. So in this case, our x sub I is equal to where you start at 0 plus delta x, which we already have, is 3 over n times I, the counter. So as it turns out, we get x sub I is equal to 3i over n. So now we have x sub I. Okay, so scrolling down. So now we have the integral, the definite integral from 0 to 3 of x cubed minus 6x dx is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of f of x sub I delta x. So then filling this in, this is equal to the limit as n approaches infinity of the summation from I is equal to 1 to n of f of 3i over n times delta x, which is 3 over n. Okay, now you have to understand with summations, in the summation, magic pen, in this summation, oh, I covered it, I didn't want that magic pen. In the summation, and what is happening here? In the summation, there it goes, one of the translucent highlighter, but in the summation then, I is the variable that's going to change the input of your expression. It'll go from 1 to 2 to 3 to 4. So the n is like a constant. The n is a constant. So we treat it just like that. It is a constant. I lose my pen. Lost my pen. So many little things in life, right? You can't lose your head over them. Okay, there we go. And we're back. So straighten that up and okay. All right, so now what I'm going to do is I'm going to rewrite this expression, but I'm going to take the limit. Now I need a little more space, so I'm going to take this and move the equal sign over. So I have this equal to, just a second. I'm going to bring out that constant 3 over n in front. I'm going to bring it out in front of the summation because it is a constant. Or we treat it like a constant because it's not got an I in the expression. So I have the summation from 1 to n of f of 3i over n. Okay? So now what I'm going to do is I'm going to put the expression for f of x in the mix there. So I have the limit as n approaches infinity of 3 over n times the summation of I is equal to 1 to n. Now I need to put in the function. It's the highlighter. So I need to put in the function where I have the function of that x expression, 3i over n. So with this, then it becomes, remember, it's x cubed minus 6 times x. So that'll be 3i over n inputted for x. Okay? All right, so now rewriting that expression, we have the limit as n approaches infinity of 3 over n times the summation I equal 1 to n. And remember, we're taking the limit still. So what do we have here? We are going to cube the first term that we see here. So we cube that and we get 27i cubed over n cubed, 27i cubed over n cubed, minus we have 18i over n, 18i over n. So we're still taking the summation. And then on the next step, I'm still taking the limit out front as n approaches infinity of 3 over n times, let me see, what do I want to do here? I've got, did I make a mistake there? I think, no. Okay, got that. 3n times, I'm going to make it 27 over n cubed times the summation. I'm going to split these summations up. I cubed. So then I'm going to write this as the difference. I'm going to take this 18 over n, and then take the summation from I is equal to 1 to n of just I. I'm going to extend this page just a little. And now, so now I'm taking the limit as n approaches infinity. I'm going to take and distribute this 3 over n to both, let me see, summations that are separated here. And what do we get? We get 3 times 27, so it looks like we get, I'm going to put a parenthesis here, 81 over n to the 4th times the summation of I cubed from I is equal to 1 to n minus, then over here I'm going to have to distribute the 3 to the 18, giving me 54 over n squared. And then that would be times the summation from I is equal to 1 to n of just I. And there's the end of the day bell, but we're going to finish this problem. So now we have those little formulas. The summation of I cubed is equal to n plus 1 times, n times n plus 1 is equal to n times n plus 1 times 2n plus 1 over 6. And then the summation of I, of course, is equal to n times n plus 1 over 2. We're able to substitute these. Remember, these are the limits. But the formula is if n is finite, you can just plug in as we practiced in class. So now we have the limit as n approaches infinity of 81 over n to the 4th power times this expression. Let's do the magic pen. So this expression that you see here is then going to turn into, do that. I think I can undo that. Oh, cross the X. That will then turn into, how do you like that spotlight? the limit, this will be then the limit as n approaches, did I just lose some stuff here? No, I guess not, no. Infinity of 81, here now, here's the big parenthesis, over n bracket, n to the 4th, times, we're just going to use the expression over to the right of n times n plus 1. Oh, you know what, that's not, oh, let me go back, crazy math teacher. Here, this is actually I squared, oh, right? That you have the summation of I cubed. It's all right, you're in a hurry after school. So the summation of I cubed is actually n times n plus 1 over 2, and then that would be squared. So let me go back to fill that in. Okay, so we have this, the summation of I cubed, I squared, I cubed. So then we would need to put in n plus 1 over 2, and then we'll be squaring that. So that will be equal to the summation of I cubed. Okay, so then continuing, we have that's minus, we have 54 over n squared, and then that would be times n plus 1 over 2. So now, simplifying a little, we have the limit as n approaches infinity of, it turns out we get 81, of course we could use 81 over 2, 81 over 2 and just leave that there. And then it would be times, we would have, if we squared this, it turns out that we're going to get n squared plus n, but that after you multiply that then, you would essentially have an n to the 4th power. Well, we can do it off to the side. Let's do that off to the side quickly. So if I have n squared plus n over 2, and I square that, n squared plus n, I get n to the 4th plus 2n cubed plus n squared. That would be then over 4. So bringing that in, okay, so we're going to have 81 over 2 times n to the 4th plus 2n cubed plus n squared over, I'm going to bring that n to the 4th here over here, put it underneath the denominator. In other words, just using the commutative property. Now, some of you are reflecting back on chapter 4 with limits at infinity, and you'll get this answer right away. The 2 goes into 54 27 times, so I now have 27. And then I have n squared plus n, and then that would be over. I'm just going to put the n squared underneath that. So now we're taking the limit as x approaches infinity, so going purple for the win here, though I used to be a Vikings fan. More like an Eagles fan now. All right, so the limit as n approaches infinity then is 81 over 2. Do I just want to say the answer? I think I just want to say the answer. I don't want to drag this out any longer than I have to. So we recognize that we have the power. Let me highlight these powers. Let's go to the first one, and we say, we have an n to the 4th over n to the 4th. That is the same degree in the numerator as it is in the denominator. Therefore, I look at the coefficients of their leading terms. And I look over in the second fraction, and I have, that's an n squared over n squared. The degree of the numerator is the same in the first fraction, where I have the yellow highlighted, and the degree of the numerator and the denominators are the same in the fraction where I have the blue highlighted. So I'm looking at the coefficients of their leading term, which are 1 and 1 in both cases. So the ratio or the quotient of their coefficients is going to be 1. 1 over 1 is 1. So we get the limit as n approaches infinity as 81 over 2 times 1 minus 27 times 1. So we calculate that, and we get 81 over 2 minus 27. It turns out to be negative 6.75. And this would be the net area. Remember that you have some negative and some positive area. Now this is the theory and kind of like a proof, but you need to understand this. So I went through it. You can review this if you like. And the second part that I showed you then, or rather the third part, let me add another screen, is where you took the actual area, and that was the actual, that was the actual area, which we know to be negative 6.75. But when you're looking at this in terms of the definite integral, we know that the definite integral went from 0 to 3 of x cubed minus 6x dx. So then to find this, we computed the definite integral. The definite integral if you recall from class, was that this was equal to the antiderivative evaluated at 3 minus the antiderivative evaluated at 0. So when we compute this, you have to remember that the antiderivative is really, you'd say, f of 3 plus c minus f of 0 plus c. When it turns out, when you compute the definite integral, the c's are going to cancel, so it doesn't matter what the constant is, it's just going to cancel. So you just evaluate f of 3 minus f of 0. So when we do that, then we have our antiderivative. So we have, I'm just going to write the whole thing, 0 to 3 of x cubed minus 6x dx is equal to capital F of 3 minus capital F of 0, which means we are taking the antiderivative and evaluating at each lower limit. If you recall, the lower limit and then the upper limit. So we have the following. We have this is equal to then x to the 4th over 4 minus 6x squared over 2, which is then going to be 3. So I'm going to just simplify that. So it's going to be 3x squared. And then we're going to put a bracket around it, and we're going to say from x is equal to 0 at the lower limit to 3. That will then equal f of 3. So here it is. 3 to the 4th over 4 minus 3 times x squared. So it'll be 3 times 3 squared. Minus, so we'll take that's f of 3. So when you see this, here's f of 3. This is the antiderivative evaluated at 3. Then we have f of 0, and we're going to put the antiderivative evaluated at 0. And some people are already thinking that, I don't even know why we have to do that. Sometimes you realize that the f of 0 is 0, but you must be careful because it is not always going to equal 0. So you can see at this point that is 0 because we have a polynomial. And when you evaluate a polynomial at 0, when there's no constant, of course it's going to be equal to 0. There's no plus c or plus a constant on the end. So we get our final answer here now of, what do we get? Looks familiar because what is it? It's 81 over 4 minus 3 times 3 squared is 27. And what do we get when we divide that? Is that the right value? 81 over 4 minus 27, and that turns out to be equal to, it should be negative 6.75, I'm hoping it is. So check that with your calculator, negative 6.75. And it is correct. And there's a C value. All right, Saucon's playing tonight, so wishing good luck to all the football players. And if you hear this on Sunday, I hope there's good news. But if not, remember, we either win or we learn. And you guys have done an awesome job this season, all you football players out there who are listening to me. And have a good weekend. I'll see you next Monday. Actually, period 3, I'll see you next Tuesday, but you can stop off. Bye-bye.